Okay, and then for this last one, what I'm going to probably do is go ahead and clean up our function first of all, and then we'll go back taking the integral of it. Meaning that we have a quantity squared, and so if we square out that base, then we're looking at the integral from 0 to pi over 6, making sure I write 0 this time. Let's see, it'll be secant squared x minus 2 secant x tangent x, and then plus tangent x squared. All of that dx. So now we can kind of go down the line a little bit and then do the integrals as we go throughout it. Okay, so if we were going to go term by term, I know I have a formula for the integral of secant x, so we can do that. I have a formula for secant x tangent x, but do I have a formula for the integral of tangent squared x? I don't, so let me go through and make a substitution. Going back into, again, your world of your basic trig identities. Remember, you have like sine squared plus cosine squared equals 1, where we have an identity for tangent squared. We can replace tangent squared with secant squared x minus 1. We're going to have to do that because we don't have a formula to take the integral of tangent squared. Okay, so really for this problem, I'm looking at the integral from 0 to pi over 6. It looks like of 2 secant squared x, and then minus 2 secant x tangent x. And then that last term, then we'll just do minus 1 dx. Okay, so going back through here then, I do have a formula to take the integral of secant squared x, that's good. Also secant x tangent x, and of course we can do 1. Okay, so now it looks like we're ready to go. Let's go piece by piece. If I pull off the 2, then I know that the integral of secant squared x is just tangent x, because our angle is just x. And we're going to evaluate that from 0 to pi over 6. Okay, if I pull off the 2, the integral of secant x tangent x is just going to be secant x, evaluated from 0 to pi over 6. And then the integral of just 1 itself will be just x, evaluated from 0 to pi over 6. Okay, so let's go through and plug in the upper bounds. Pull off that 2. So we're looking at tangent of pi over 6 minus tangent of 0. Minus 2, and then we're going to go secant of pi over 6 minus secant of 0, and then minus pi over 6 minus 0. Okay, let's just clean this up then. Well, the tangent of at pi over 6 is going to be the square root of 3 over 3. I'm going to mark those up. The tangent of 0, that's just 0 over 1, which is 0. Secant so the reciprocal of the x value at pi over 6 will be 2 square roots of 3 over 3. The secant, the x value at 0, the reciprocal of the x value at 0 is 1. Okay, and then we can kind of keep going through here just a little bit. So because I'm kind of running out of room, let me just come below here just for a second. So if I distribute it in here, we'll get 2 square roots of 3 over 3 minus 2 times 0 is 0, minus 4 square roots of 3 over 3 plus 2, and then minus pi over 6. Okay, and now just to kind of just working on combining some like terms and finishing this up, I'm going to go back through this problem just 1 second, make sure everything looks great. Oh, here, hey, did y'all notice this at all? Right up here, when you're squaring out your function, 2 positives, terms multiplied together, is going to make that a plus sign. Let's put a plus right in there. Hey, isn't it great to go back and check your work? So we put a plus right there. A plus. Luckily, that's not going to really change much of anything in our work so far, other than the fact it's going to make that term positive. Okie doke. So these have, and I think everything else looks good. Y'all are going to have to check me on this stuff. But 2 square roots of 3 and 4 square roots of 3 will be 6 square roots of 3 over 3 plus 2 minus pi over 6. And last but not least, why don't we just kind of reduce this first fraction? We'll write it as 2 square roots of 3 plus 2 minus pi over 6, and we'll call that finished. And that is what's making up our area between secant x plus tangent x squared between 0 and pi over 6. All right, let's hope that all my other sign changes are pretty good so far, but I can always check all that stuff for you guys later. Okay, let me erase some stuff and let's get on to example number 2. Okay, here in example 2, we're going to find also again the integral underneath the curve from -3 to 1. And it looks like just kind of we did it on our last problem. Let's clean up this problem. Let's clean this up just a little bit first. So let's write it as an integral from -3 to -1. Let's go y to the 5th over y cubed, so it'll be y squared minus, let's say we can write that either as 2 over y squared, or we can say 2y to the -2. Put that in parentheses and then dy. Now by writing your function more like this, now you can see it as going kind of term by term, and we can take the integral that way and find the antiderivative that way. Okay, so the first term, I want to take the integral of y squared. We always add 1 to that exponent and divide by the new exponent. And we're going to evaluate that from -3 up to -1. Then minus 2, and the integral there would be add 1 to your exponent, so y to the -1 over -1, evaluated from -3 to 1. Okay, so cleaning this up just real quick before we actually go about the process of taking or plugging in our endpoints. Let's write that as 1/3 y cubed, evaluated from -3 to -1. And it looks like here now it's going to be plus 2y to the -1, evaluated from -3 to -1. Okay, so it's 1/3. It's the upper bound, so -1 cubed minus the lower bound, -3 cubed, plus 2. And the upper bound, so -1 to the -1, minus the lower bound, so -3 to the -1. Okay, further cleaning this up, we can write -1 cubed as just being -1. We can write -3 cubed as being -27. -1 to the -1 is just -1. And then -3 to the -1 will give us a -1/3. All right, let's put these together and kind of distribute some stuff in there. So inside this, basically this first parentheses, then you have 1/3, you have a -1 minus a -27. So -1 plus 27 is 26. Plus 2, we have a -1 plus a third, or you can think of it as 1/3 minus 1, which is a -2/3. Okay. And going back and just checking one more time, looks like everything's good before we go to get our final answer. Okay, I think everything looks good. Hopefully y'all agree with me to this time. We have 26 over 3 minus 4 over 3, so we'll get an answer of 22/3. And that right there is going to represent the area of the curve for that function. All right, example 3. Okay, so for here in part A, what we're doing is we're taking a function going from 1 to sine x of 3t squared dt. And the first thing they want to do is in part A is we want to evaluate the integral first, and then we're going to differentiate the results. Okay, so let's evaluate the integral of 1 to sine x of 3t squared dt. Okay, well if I pull off the 3, the integral of t squared would be t cubed over 3, evaluated from 1 to sine x. So canceling out those terms, really we're just looking at now putting in the top term, which would be sine cubed x, minus the lower term plugged in, which is just 1 cubed, or sine cubed x minus 1. And now they say we want to take the derivative of that. So d dx of sine cubed x minus 1 is going to give us a 3 sine squared x, and then the derivative of sine of x is going to be cosine x. And since then at that point, the rest of it is just the derivative of -1, which is 0. So we get a final answer of 3 sine squared x cosine x. Okay, so now as we go on to part B in this problem, we're going to try to get the exact same answer, but we're going to do it through a different way. We want to first differentiate the integral directly. Okay, so if you guys pause this video for a second, and let's go back up to where it talks about the fundamental theorem of calculus part 1. Okay, because that fundamental theorem of calculus part 1 says that if I take the derivative with respect to x of a function that goes from a value, say a, up to x of the function, then we get just the original function as is. Okay, well if I look up here, I'm basically saying if I take the derivative of this, then it's saying I should get this function. But that's not our answer right here. And also the fact of my upper bound, instead of being an x, is a sine x. We've got to do some changes around here in order to get this, in order to use this whole property right here. I've got to look at changing, quote unquote, or substituting the upper bound. So what I'm going to do is I want to break this problem in almost to two pieces. Let's let y equal the main function itself, which is going to be the 3t squared, okay, dt, and then let's let u equal the upper bound that we have, the sine x. Okay, so now to keep kind of using that whole theorem so we can get this going on, I want to notice how it says the derivative with respect to x, and x is my upper bound. Well, now my upper bound's u, so now I'm going to go du from my lower bound is 1 up to u of my function, so 3t squared dt. And now what I want to do is I'm going to multiply all of this times du dx. Okay, so that way what it gets me is a d dx, because the du is going to kind of cancel with that du back there, and then, sorry, I should put a dx right there. Okay, so keep it on going through the substitution process. This portion right here now matches exactly what the fundamental theorem should say. The derivative with respect to x, or d du, going from any number up to u, I'm going to get the function back just as is. Okay? So at this step right here, then we can just write it as that whole part right there. I'm going to get my function back as is. So it's just going to be 3u squared, then times the du dx. And in just one more step, we can have this all finished. Because what we just need to do is plug in what u is. Going back up here, what we decided was that upper bound. So this will be 3 my u squared, so sine squared x. And then what is du dx? Well, let's go up to what u was and let's take the derivative of it. That's what that's saying. So du dx, the derivative of sine, is cosine x. So let's just put that down there right next to the sine squared x, and we have our answer. Okay, so basically what we did is when my upper bound was not just a plain x, it was a sine x, I always just let u equal that. Okay, so I let u equal sine x. We're going to then take it from 1 to u as opposed to 1 to sine x, just going 1 to u. We set it all up in terms of that derivative. It just keeps basically this the way it exactly was. All we have to do now is just plug in u where t was, and then multiply it times the derivative of u, and then you're good to go. And we get the same answer in both spots, whichever way we do. Obviously part A was a little bit easier, but you know, we can do it a second way if we have to.